Exploring the Solar System Part 4, Exoplanets. Exoplanet, short for exosolar planets. In other words, planets going around stars that are not our sun, but other stars in the galaxy. We hope that not only is it interesting to look at those planets around other stars that might be interesting in their own right, it might also help us understand our own solar system. So there's a certain cross-feed. If we look at exoplanets, can we learn more about our solar system? And can we use our knowledge of our solar system to learn more about solar systems that are out there in the galaxy? So why should we look for them? Well, A, it's interesting in their own right because ultimately, maybe, there's not only interesting solar systems in terms of just understanding how planets evolve. Who knows? Maybe there's life out there. We are exploring our own solar system. We're looking for life on Mars. We're looking for life on the moons of Jupiter. But maybe there's life on exoplanets going around other stars. Maybe those stars are close to us. Maybe those stars are a long way away. But life might be out there. It's worth having a look. So I'm going to say a little bit about how we find these planets. And right at the end, I'll just say something very briefly about how we actually try and figure out whether there's life out there or not. And again, I'll be asking, where do we go from here? What's next? So the orrery at the front here has been moving in the last hour or so, reminding us that we have a number of planets. We have 8 planets and a whole load of dwarf planets and a whole hundreds of moons going around our sun. But is that typical? Is that what we would expect to find if we were to look at solar systems elsewhere in the galaxy? Are there other planets like Earth? We're not restricting ourselves to saying life can only exist on an Earth-like planet, but it would still be interesting to know if there's an analog, if there's an equivalent of Earth out there. How many planets out there look similar to the Earth? And ultimately, can we get a handle on the idea of whether or not there is life out there in the galaxy? It's going to be difficult to get the answer yes or no, but at some point we will get a signature that yes, life is out there somewhere. And ultimately, maybe, we hope, studying other solar systems, if nothing else, will help us get a better handle on our own solar system. So there are a number of ways we can actually find planets orbiting other stars. Of course, it's easy to see planets orbiting our star because all we do is look up and night after night we see some of these objects moving in the sky. But how do we do it if the star in question is not our own sun, but is a star light years, or tens of light years, or hundreds, or thousands of light years away? How do we find these planets? There are a number of different methods. We can look for how a planet going around a star makes the star wobble slightly. We can look for a planet that happens to pass in front of the star and change the amount of light that we see from the star. It's possible, if you've got the right sort of equipment, although the planet is very much fainter than the star because it's just basically reflected light from the star, if you can block out the light from the star, perhaps you can see the planets around them. Rather technically challenging, but possible. I'm going to mention these 3 techniques. There are others which I'm not going to say anything about. The way light gets bent, so-called microlensing, and also astrometry. So those are mentioned in the handouts that you can pick up if you wish, but I'm not going to say anything particularly about them this morning. So this idea of using wobble, because a planet going around a star will make the star move, because they both orbit around their common center of gravity, then you might not be able to see the planet, but if the star is sometimes coming towards you and sometimes going away from you because of the wobble induced by the planet, then it's possible to pick that up by looking at the spectrum, the light that's coming from the star. Here, again, we've got a cartoon of what it would look like from above as the planet goes around the star. It makes the star wobble slightly. The star moves in a small circle, depending on the mass of the planet. So as seen from the side, it would go backwards and forwards. But the important thing as far as the wobble technique is concerned is that some of the time the star is moving towards us and some of the time the star is moving away from us. And that means if we look at the speed of the star, it goes forward, it goes positive and negative, away from us, towards us, away from us, towards us. And if we look at what that does to the spectrum, there's a shift, which we call either a red shift or a blue shift. Parts of the spectrum get shifted towards the red end of the spectrum or towards the blue end of the spectrum as the star moves towards us or away from us. It's called the Doppler shift. It's been known for a long time. You've heard police sirens or ambulance sirens. They have a high pitch as they come towards you, and then it goes to a much lower pitch. The waves get stretched out as the object is moving away from us. It's the same idea. But because taking a spectrum is relatively easy, as long as the object is bright enough, you can get very accurate shifts towards the red or the blue, so you can see relatively small changes of speed of the star. How much can you actually get in terms of the state of the art for using spectroscopy on a telescope? Well, you can note changes of speed of the star towards you or away from you, which are as small as a few centimeters per second. In other words, a very slow walking pace could be picked up in terms of the speed if you've got a bright enough star and a sensitive enough spectrometer. So you can get tiny changes to the star, and from that you can infer what planets are going around the star. The second technique is the transit method, whereby, again, if we imagine a hypothetical planet, if it's aligned correctly, then occasionally the planet will go in front of the star. In which case, if we make a note, if we record how much light are we getting from that star, it'll generally speaking be constant, except when the planet goes in front of the star, in which case the amount of light will fall. Only by a small amount. If the planet is small and the star is huge, then the amount of light that we lose by the planet effectively being silhouetted against the star is going to be quite small. A large planet will block more light from its parent star, and so when we look at how much light is blocked by the planet, a large planet will have a big dip, whereas a small planet on the right-hand side will have a relatively small dip. Even a large planet, it's not going to be huge. It's not going to drop by 10%. It's going to drop by 1% or 0.1%. You've got to have very accurate measurements of the light output of a star to see the tiny drop that you would expect if a small planet drifts in front of the star. But even if you've got multiple planets, you can still use this technique. It gets a little more confusing, but if we imagine a star with multiple planets going around it, we would see the light from the star drop, and then one planet would go off the edge and the light would come back again. But then if we had, for instance, two planets that happened to go in front of the star, we would see the light drop and then drop again and then come back again. So it can get rather complex, but if you have this so-called light curve, you can then deduce what planets must be going around the sun and how large are they, how much light do they block from the star, and how long does it take. If we see this pattern repeated again later, how long is it for each planet to go around the star? So we can get information about the solar system by looking at these light curves. This is an actual set of data, again the same idea. That's what we would expect to get, the white curve. The blue dots are what we actually see. If we measure the light output of a star, what we tend to see is we see a drop and then we say, well, what is the best model we've got for how that appears to be changing? And then we use that to infer the existence of a planet going around the star. So this is actual data from the James Webb Space Telescope. So again, you probably can't read it, but this is the normal output from the star, 100, and then it drops as some object goes in front of the star, and in this case it drops to about 98.5%. So it's only dropped by 1.5%, but if you have very accurate measurements of the amount of light from the star, you get an accurate indication of how much it's dropped, you get an accurate indication of how big this planet is, and you watch for these dips coming around periodically, which tell you you've got not simply a sunspot on the star, that you've got actually a planet going around the star. The third technique I want to mention is the direct imaging. Let me just run that video again. What you've actually got here is a very bright star and a very faint planet, but if you block the star out, if you use an occulting disk to block the star, then hopefully you'll be able to see the very faint planet. Normally, it's so faint, it would be completely washed out by the star itself. It's been often likened to, what if you had a tiny little firefly, but it was sitting right next to a spotlight? It would almost be impossible to see unless you can block the spotlight on, and then you can see the very faint firefly next to it. So it's a very technically challenging idea, but if it can be done by either having a blocking disk and occulting disk inside the telescope, or another idea is you have the telescope and separately you have a blocking disk which you then place in front of the bright star and you see what's left. So that can be done. And here are images taken from a star. The star itself would be in the middle, but it's been blocked out by this occulting disk, and what you're left with is a whole load of dots. This one doesn't appear to be moving very fast. Presumably that's a planet a long way from the star. But again, if I run the animation one more time, I hope you can see that that is effectively this picture of the orrery taken from above. It is a solar system with planets moving at different speeds because they are at different distances from the star. So we can deduce by direct imaging that this is a solar system of at least 4 planets, perhaps a few fainter ones that we can't see, but we can at least deduce there are definitely 4 planets in this system. And in this particular case, we seem to be looking down on it directly from above. In some cases, we see systems where we see them from the side. And so we don't see the star here, we don't see the planet when it's too close to the star, but when the planet does poke its head above the parapet, we see it coming either side. It's a bit like looking at the orrery from the side and watching the planets go round. Too close to the star, it disappears, but we can see where that object is. These time lapses were taken over many years, so we can see the complete passage of these planets. The James Webb Space Telescope is able to do a certain amount of direct imaging. Again, when we point at a star, this is a very bright star. It's been blocked by this black disk, this occulting disk right at the center. So the star has been taken out, and the question is, what are we left with? In this case, we don't seem to see individual dots. We're not seeing individual planets. It looks like this is a star in the early stages of its formation. So what we have is all of the gas and the dust in which planets are ready to form. So we think this is an early so-called debris disk. This is the leftovers after the star was made, and it looks like something is starting to form structure in there. It's not a uniform pancake, which you might expect from just a dust collection. It looks like there are rings, the bands, if you like. It's a little bit risky perhaps, but it's a little bit like saying, I can't see any planets, but it looks a bit like we've got an asteroid belt. And it looks a little bit like we've got a Kuiper belt. And something else is making gaps in this structure. It's not uniform. Something is forming this ring structure in this disk. And it might be something like an asteroid belt or a Kuiper belt. It might be that we've got a number of gas giants in there that are starting to form and starting to change the way this disk is evolving. So direct imaging is a way of seeing planets evolve, and it's a way of seeing planets that are mature in a solar system, much like our own solar system. One advantage of these techniques is especially true if we use them in combination. So for instance, we've got the various techniques like the wobble technique and the transit technique. The wobble technique depends on the mass of the planet. A big planet like Jupiter will make the sun move quite a lot, and a big equivalent of Jupiter in an exoplanet system will make the star change, and the bigger the mass, the bigger the change. So by measuring the change, we can infer what the mass of the planet is. And with transits, we're effectively saying when an object moves in front of the star, the size of the planet will determine how much of the light from the star is blocked out. So the bigger the planet, the more the drop. So by looking at how much the light is decreasing, we can get the size of the planet. So if it is possible to use both techniques on the same solar system, then for a given planet, we can determine its mass by how much the star wobbles, and we can determine its size by how much light is blocked when it moves in front of the star. And if we have the mass of a planet and the size of a planet, then we can infer its average density. And we can figure out, is it made of something the density of water, or is it made of rock, or is it made of metal, or is it made of something else? So it's really useful to be able to use more than one technique, because as soon as we have the density of a planet, we've got an idea of what type of planet is it. Is it a rocky planet like the Earth? Is it a big gas giant like Jupiter? Spectroscopy will tell us something about the atmosphere. I'll come to that in just a second. And if we know how far the planet is from its parent star, and we know what type of star it is, we can guess or calculate how hot that planet must be. If it's very close to its star and the star is very bright, then it's going to be a very hot planet. If the planet is a long way from the star, or the star is quite dim, then perhaps it's going to be a very cold planet. So we can use the idea of temperature to tell us, are we talking about an icy world? Are we talking about a water world? Are we talking about a lava planet? So all of these little bits of clues can tell us about what planets are there. And this is an indication of some of the exoplanets that we've found so far. I say some because we've found approximately 5,000 planets out there in the galaxy. This is only about 1,000 of them. So this is just a representative collection of some of the thousands of exoplanets that we know about. They're plotted here. The vertical axis doesn't mean anything. They're all approximately to scale in terms of their size, and they're arranged from very cold ones on the left to very hot ones on the right. So there's a temperature scale going along this way. Anything out here is something like minus 200 degrees. Anything a little closer to the middle there is closer to plus 200, roughly speaking. So there's a Goldilocks zone of where we would like a planet to be if we want that planet to be nice and temperate, like the Earth, for instance. And just to give you a sense here, there's a few solar system planets thrown in here. So in the bottom left-hand corner there, we've got Jupiter, Saturn, Neptune, Uranus, just to show you that the solar system planets are in there. I know they're not exoplanets as such, but just to give you a sort of sense of scale, as it were. So if they're really cold on the left, like Jupiter, and really hot on the right, the Goldilocks zone where we would think that's just about where we would want a planet to be if we want, for instance, liquid water to exist such that we had oceans and an atmosphere and water vapor in the atmosphere, which would be conducive to life, then we say, well, actually, the Goldilocks zone is actually relatively small. We wouldn't want to exist on the left-hand side, and we wouldn't want to exist on the right-hand side if we're looking for life. It is possible, remember, that even around a planet like Jupiter, the moons might be in the right position, but this is just looking at the planets themselves. If we think about where our planets exist, Mars is just a little bit too cold, Venus is just a little bit too hot, and not surprisingly, the Earth is just in there. The Earth is actually a planet there. So the Earth is indeed in the Goldilocks zone, which is no surprise because the Goldilocks zone, if you like, is almost defined by the fact that we are in the right place for us to exist, the anthropic principle. But if we have a look at some of these other exoplanets, let me just say a little bit about some of these rather interesting ones. There are some very exotic planets out there. What I found quite surprising was the fact that we look for exoplanets. How likely are we to find them? 20 years ago, we didn't know. We didn't know whether or not it is likely that other stars have planets. Now it looks like pretty much every star has a planetary system. Even the one that's right next door to us, Proxima Centauri, only 4 light years away, that has a planetary system. Are we just lucky that the nearest one happens to be also occupied with planets, or does it mean that they are basically ubiquitous? It looks like, as far as we can tell, it is very common for stars to have planets. There's a few interesting categories up here. The top left there is the Methuselah planet. That appears to be 12.7 billion years old. That is much older than the Earth. If you bear in mind that the universe itself is only 13.8 billion years old, this planet came into existence not long after the Big Bang. So it looks like in the very early universe, stars were made very quickly, galaxies were made very quickly, and even planets showed up very quickly after the start of the universe. Our star, the Sun, didn't come along until a few billion years later, but it looks like other planets came along a lot earlier than our Sun and our Earth. In the top right-hand corner, we have one that is very close to its parent star and is really, really warm, 4,000 degrees. It's difficult to imagine any planet at that sort of temperature, but all of these ones on the right are really hot, mainly because they are so close to their parent star. The one in the bottom right is so close to its parent star, only a few million kilometers, it's actually egg-shaped. You notice the actual shape of it. That's a genuine indication of what we think the shape of that planet is. It is so close to the star is stretching out the planet into a sort of rugby ball shape, an egg shape. There's a couple of interesting ones again. This one here, which goes under the ridiculous name of HAT P67b. It is huge. It is much, much bigger than Jupiter. Jupiter is a really big planet in our solar system, but this is even bigger than Jupiter, but its mass is less than our Jupiter, which means it must be really low density. It's been likened to, well, this planet must have the density of marshmallow, basically. It's a very low density compared to, for instance, the rocky Earth. But even though HAT P67b is a ridiculous name, I think the prize for the very best name of any exoplanet has to be Coconuts 2b. What a fantastic name. That is a great name for an exoplanet. Coconuts is a sort of a rather engineered acronym meaning cool companions on ultra-wide orbits. In other words, planets that are on huge orbits a long, long, long way from their parent star. 7,500 astronomical units. So Earth to Sun is 1 AU. This object is 7,500 AU from its star. Instead of taking a year to go round its star, it takes probably more than 1 million years to go round its star. Imagine seasons that lasted 250,000 years each. And I think my favourite so far, they're of course finding them all the time, but one of my favourites is this one. Again, not a very good name, LHS 1140b. This appears to be an ice world based on its density, based on its distance from the sun, but it's locked to the sun as far as we can tell. It always faces, one face of this planet always faces its star. So although it's an ice world, the side that is always facing the star is probably melting, which means it's an ice world, but on the spot directly in front of the star, it's probably water. So you either think of it as ice with a little bit of water, or you think of it as an ocean that's completely surrounded by ice. But effectively, it looks like an eyeball. That's, of course, an artist's impression, but that's what we think it might look like. Essentially, all ice, except for the point that's facing the star and always facing the star, and that would probably melt the ice into an ocean. So it gives this wonderful eyeball ocean planet. There are a number of spacecraft that are currently looking for exoplanets. Gaia is looking at where stars are, and it might see the stars wobble and deduce there are exoplanets. JWST, the James Webb Space Telescope, has been told, go and look at this system, go and look at that system, because we think there are planets forming there. That's one of JW's jobs, is to actually look at planet formation. There are a number of other spacecraft missions, some old, some yet to be launched. One of them I find quite interesting, the Roman, named after Nancy Grace Roman. That mission is one in which they're going to try some direct imaging, but instead of having a little occulting disk inside the telescope to block the star and then look for any planets that are around it, they have a different idea. They haven't decided to fund this yet, but it's a very interesting idea. You have the telescope separate from the occulting disk. You separate and then you expand this occulting disk until it's 100 meters in diameter, and then you fly it into the far, far, far distance, such that it's just big enough to cover a star, but not the planets that go round the star. So you fly it 50,000 miles away, and then it will block the star and hopefully allow you to see any planets that are going around the star. A very ambitious idea. It needs very careful station keeping between the telescope and the occulting disk 50,000 miles away, which has to be kept in just the right position to block the star and allow you to see the planets. And it needs an enormous amount of origami to pack a sun shield, effectively a star shade, 100 meters in diameter, but you've got to pack it into something the size of a barrel, something like that. So it's just like the problem with the origami of unpacking the sun shield of the James Webb Space Telescope, the same sort of idea. Let me finish, because I'm slightly over time here, let me finish with the idea of how do you find life on other planets? Well, if you've got a planet transiting, for instance, it might go in front of the star, or its orbit might take it behind the star, you'll get a dip in light as it goes in front of the star. And you might also see a change of light when the planet goes behind the star. In both cases, in principle, you can take the spectrum before and after and see, are there any changes? Any change you see when the planet disappears in the spectrum tells you that light came from the planet because the planet is no longer visible. Or if the planet is in front of the star, some of the light is going to come through the atmosphere, if there is one. If the planet has an atmosphere, some of the sunlight will come through the atmosphere, and again, you look for any changes you can see in the spectrum. So this is actual data from the James Webb Space Telescope. They've looked at how much the light dips, and they've looked at different wavelengths. So each of the colored dots corresponds to how much does the light dip at different wavelengths. And you can see perhaps that for the wavelength corresponding to the red dots, it dips a certain amount, but it dips more if you look at the wavelength corresponding to the yellow dots. If you do that for a number of different wavelengths, you can build up a spectrum of what chemicals are present in the atmosphere of this star. In other words, you see peaks corresponding to water or carbon monoxide or sulfur dioxide. And so you can start to actually figure out what is the composition of the atmosphere of a planet going around a star thousands of light years away. The fact you can figure out the chemistry in the atmosphere of a planet around a star thousands of light years away is truly amazing and is a testament to the instrumentation on board the James Webb Space Telescope. Let me finish by giving you an indication of what we found so far. Each dot on this particular graph is going to be a planet whose mass is given by this vertical axis and the how long does it take to go around its star on the horizontal axis. In the 1990s, we hadn't found that many planets. As soon as we go into the 2000s, we start finding more. As soon as we go to the late 2000s, early teenies, the Kepler spacecraft is starting to find lots of objects via the transit method rather than via the wobble method. And now we are finding hundreds, thousands of exoplanets. So our own planets are there just for reference, but notice that we don't really see that many Neptunes. We see quite a few Jupiters up here. We don't see many Earths and we don't see many Neptunes. But that doesn't mean they're out there. It just means Jupiters are easier to see. Jupiters are big. Jupiters are massive. They make the star wobble a lot. They block a lot of light. So we have to remember that this is a biased set of data because it's always going to be easier to see Jupiters than it is to see Earths. We think Earths are out there. There is definite evidence that there are some planets similar to Earth, but most of the data we have is on big planets like Jupiter. And notice a lot of them are quite close to the Sun. Same argument. They're easier to see if they're close to their parent star. They produce more of a wobble. So small planets a long way out are going to be difficult to find. We think they're there, they're just difficult to find. So a reminder that if you're interested in exoplanets and what is out there, NASA have a very good page of these are all of the exoplanets we found to date, all of the 5,000 of them. There's an archive of all the data, and there are new missions coming online in the next few years that will be telling us more and more about exoplanets, which hopefully will give us more information about is there life out there, and even if there isn't, it'll give us more information about how our own solar system works. Thank you very much.